Okay, so we will get started with a pre-lab lecture. We're still in our last section, and the online lab for 236 deals with the carbonyls, as you have seen. We got started with that last week. We are with the Grignard reaction. Now we're moving on to a reduction reaction of the carbonyl. This is with sodium borohydride, and it's a very popular reaction that we perform in the lab. It's quite an interesting one. It's called reduction of benzyl. What's really nice about this reaction is it's actually, you can follow it with color. Benzyl is a yellow solid. It's a pale yellow solid, and the products are colorless. So the disappearance of the yellow color is an indication that the reaction is completed. That's kind of nice if you can actually just look at a color change and say a reaction has taken place. This reaction can certainly take place with lithium aluminum hydride, but keep in mind sodium borohydride is a mild reducing agent. In the lab, if sodium borohydride can do the job, then you want to use that because it's just safer. Lithium aluminum hydride is very reactive, so reactive that it is flammable. Also with lithium aluminum hydride, you have to take great precaution not to get any moisture near it because you have the hydride ions, and if you bring any moisture, you're going to get protons, and that's going to release hydrogen gas. When the concentration of hydrogen gas goes above a certain level, it's going to catch fire with oxygen in the localized area. That's why lithium aluminum hydride is very flammable. Whereas sodium borohydride is a lot more forgiving, and you can actually use it in some large X's, and then also use a protic solvent such as ethanol. Some of it will get destroyed by the protons in the ethanol and still doesn't catch fire because it's not so reactive. It reacts with the carbonyl group to convert it into an alcohol. Now what we have here is a diketone. It's a dicarbonyl. We have a diketone, two carbonyl groups. I'm going to label them 1 and 2. It doesn't matter which one is 1 and which one is 2. So you can also call it as a diphenyl ketone. C6H5 is the benzene ring. So if partial reduction takes place, one carbonyl group will reduce. If a complete reduction takes place, then both carbonyl groups get reduced. What's interesting is if your sodium borohydride is fresh, if it's freshly purchased, I'm going to call this product A and this is B. B is going to be the product you're going to get. If sodium borohydride is old, then you're going to get A. It's really not a student-dependent thing. If students follow the instructions, and if we gave them good stock of sodium borohydride, they'll always get complete reduction. But as I went through this lab, interestingly, they have, I'm thinking everyone is getting the same thing when they ask for provisional data. The final product is a partially reduced product. But typically we get B, the fully reduced product. But anyway, when a student approaches a question, when they work with this benzyl, they don't know which one they're going to get. So very simple mechanism, as you've already seen. This is just shown with one carbonyl. What I'm going to do is show it with two carbonyls. So let's go ahead and take a look at C6H5, C double bond O. This is your benzyl. You're doing it with mechanism with actual reaction. You can just go ahead and use the sodium borohydride, the hydride, or you can use the BH4 minus, or you have a choice of using like this. This entire thing is minus, okay? Whichever one you like, but that's going to attack a carbonyl. The same thing can happen on the other carbonyl, 1 and 2. And this is going to give us C6H5, CO minus. Then let's go ahead and get this other one here. This is going to be BH3, hydride attacking that. Oh, actually, I'm going to have that attach the hydride there. C double bond O, C6H5. And then here's BH3, but keep in mind this is less than an octet. It's always looking for electrons, okay? So there's your O minus, and the O minus will form this. So this is going to be our Lewis base forming a new bond with our Lewis acid. Then we're going to add water to this reaction. We're going to heat it up, and that's going to give us C6H5, CHOH, C double bond O, C6H5. Now your BH3 goes as a variety of oxides. So typically what I'm going to do is just write one oxide here. That's BH3 becomes, these are all your side products that you're going to get from the reaction. But this is one product. And if both carbonyls get reduced, keep in mind that you will get a alcohol on both carbonyls. Okay, but this in a nutshell is the mechanism. If you don't like all this complication, don't be afraid to just take the hydride and tack it on the carbonyl. That's perfectly okay. Okay. So in the lab, you would take this yellow solid, which is benzyl. You would add ethanol, which is a solvent. You will add an excess amount of sodium borohydride because some of the sodium borohydride will react with ethanol. Ethanol has protons, sodium borohydride has hydrogen ions, so some of it will be lost as hydrogen gas. Okay, and the yellow color will become colorless. That indicates the completeness of the reaction. You either will add boiling water or you'll add water and then heat it up to finally get the product. You let it cool and then you'll get nice plate-like crystals, okay? Now, we can get a variety of products, and that's what's interesting. Now, if you get the partial reduction, you have one stereocenter, so you can get the R enantiomer. You can also get the S enantiomer. You'll get 50 of each, so what you will get is a racemic mixture. The reason you'll get 50 of each is the hydride can attack from the top and the bottom of the carbonyl. The carbonyl is very flat and planar, so the hydride can come from the top or the bottom, and that's how you get the R and S enantiomer. To get the complete reduction, you can get four possibilities. You can get RRSS enantiomers. So it can attack from the top, from the bottom. So you'll get 50 of each, and that would be a racemic mixture. So you'll get 50 of the RR and the 50 of the SS. Or you can get the RS and the SR. These are identical. These are your meso compounds. Now the partial reduction is called benzoin. The full reduction is called the hydrobenzoin. So this is the hydrobenzoin. The RRSS is called the plus minus. That's a racemic hydrobenzoin. This is called a mesohydrobenzoin. So it's kind of an interesting reaction. Students will find out whether they got benzoin or the racemic benzoin or the mesobenzoin. Here's the mechanism of the reaction, where you start with the benzyl right in the middle here. Okay. You can get the plus and the minus benzoin depending on whether the hydride attacks from the bottom or attacks from the top. Okay, so that's what happens. And then you can get the complete reduction where you can get the hydrobenzoin. So the plus hydrobenzoin and the minus hydrobenzoin, where again the hydride can attack from the top and bottom. Then you can get the mesohydrobenzoin, which is the RS and the SR. So this is the RS and this is the SR. This is the RR and this is the SS. This is the R and this is the S. So you can get all these things. You don't get these two separated. You will get it as a racemic mixture. These two are identical. No. Okay, the RR and the SS are racemic mixtures. These are identical. So keep that in mind. Okay. So you have all these varieties, which is what I labeled as 1, 2, and 3. The question is, how do you find out? And this is an important slide for you for the lab flow. You have a question on this. To get the product, you take the melting point. The melting point is 122 to 123. Then you have a complete reduction. So what you have is C6H5, CHOH. So this is your complete reduction. You see how I'm reducing both carbonyl groups. You get RR and SS. You get 50-50 of each. Then it's 122 to 123. Your job is done very quickly. But if you get a melting point of 135 to 137, then you either have complete reduction or you have partial reduction. It could be benzoin or mesohydrobenzoin. Partial reduction is going to be C6H5. One carbonyl is reduced, the other one is not reduced. You'll get R and S, you'll get 50-50. This will be complete reduction, just like the other side, the far left. It's a complete reduction, but it's not RR and SS. It's RS and SR. They are identical, they're meso compounds. So you cannot find out from the melting point whether you got benzoin or mesohydrobenzoin. So you have some choices. You can do a mixed melting point, or you can take a TLC and you can find out which one it is. Another way is infrared. So you can do a mixed melting point, you can do a TLC, or you can take an infrared. Of these, this is the easiest and the most powerful. These two, I would say, about same level of difficulty. In terms of technical difficulty, mixed melting point and TLC are about the same. IR is the easiest. If it's benzoin, it's a partial reduction, so you should see a stretch for the carbonyl and the hydroxyl. It's a complete reduction, you should not see any stretch for the carbonyl. So this would be the easiest. It would take 1 to 2 minutes for you to confirm which one is your product. Once you confirm the product, then you're ready for the yield calculations. But I want to make sure you understand this chart. Any questions on this chart? Your first job is to determine melting point. It's 122 to 123. You have complete reduction and it's R or SS. You cannot separate that. They come out as a racemic mixture. The melting point is 135 to 137. That's too small a difference for you to eliminate. 137 to 139 is very close to 135 to 137. It could be benzoin, which is a partial reduction, or a complete reduction. You have three techniques that can help you: mixed melting, TLC, and IR. When I give a choice to students, almost everyone crowds at the IR because it's a very powerful technique. It's also pretty simple to do. Once you decide which one is your product, you can get to the yield calculations. It's all a 1-to-1 ratio. You'll calculate the limiting yield. So limiting yield, once you calculate, you take the moles of the limiting reactant times molar mass of the product. So a lot of variations here. You have two options for limiting reactant. One of them is benzyl. The other one is sodium borohydride. I can tell you that you're taking a large excess of this, so I expect this to be the limiting reactant. That's how it'll turn out. Your product, it can either be a partially reduced benzoin, or it can be a completely reduced meso or racemic hydrobenzoin. Keep in mind the molar masses of meso and hydrobenzoin are exactly the same. Benzoin is going to be a little bit different. And then you're going to employ this formula, moles of the limiting reactant times molar mass of the product. That's going to give you the theoretical yield. Then you'll get to the percent yield. So what we will do now is, I'm not saying anything in the chat. So what we will do now is kind of go into lab flow. I've already generated the data here. So let's take a look. Excuse me. So amount of benzyl used in grams, amount of sodium borohydride used in grams. As a good scientist, you must calculate the limiting reactant. Benzyl will turn out to be the limiting reactant. So to calculate limiting reactant of benzyl with sodium borohydride, between the two, I just want to show you one little thing here. Now, benzyl is going to be a 1-to-1 ratio. So it'll be mass of benzyl, right, times 1 mole benzyl This would be very simple for you. Molar mass of benzyl times, you see it's a 1-to-1 ratio. So 1 mole benzyl, 1 mole, you have to determine your product first, whether it's meso or plus minus. Okay. And then this will be 1 mole product, molar mass of product. And that is not a difficult problem for you. It's a 1-to-1 ratio. Now, mass of sodium borohydride is different. It's 1 mole sodium borohydride, of course, then it's the molar mass of sodium borohydride. But it's not a 1-to-1 ratio. It is 1 mole product does not require 1 mole of benzyl. I'm sorry, 1 mole of sodium borohydride, because you got 4 hydrides. You can actually reduce 2 moles of the product, not 4, because each mole has 2 carbonyls. Each carbonyl will use a hydride. So there are 4 hydrides. You can use 2 moles of the product. So the ratio is 1-to-2 here. So that's what I didn't want you to miss. So this is going to be 1 mole product, molar mass of product. So this is the part I want you to be careful about. 1 mole of sodium borohydride can reduce 2 moles of benzyl. So here you want to make sure, you know, that you really understand that. Okay, everybody clear with that? So you can get 2 moles of the product and everything else is going to stay the same. So keep that in mind when you calculate limiting reactant. Let me know if you have any questions. Hopefully I'm not confusing you, but the product melting point is given. And this is where it gets, well, I think your lab would have been easier for you. Product melting point is 132 to 134. Melting point of the benzoin mixture is 135 to 137. Melting point for the mesohydrobenzoin is 127 to 132. So let's just jump back quickly to my other screen. Just keep this in mind. Your product melted at 132 to 134. So when you get here, 132 to 134 are false here. So those are very close numbers, okay? So 132 to 134, you can't really say it's benzoin because, you know, it can be a little off. You know, 137 can come as 134. Don't, because everyone is using a different melt temp. This is, you know, it's just different. So your product could be benzoin or mesohydrobenzoin. So it could be partially reduced or fully reduced. Then what you do is you take your product, you mix it with benzoin, and you run the melting point. So what you're doing is a mixed melting point. In case you missed that, I just want to point that out. This is mixed melting point. What are you mixing? You're mixing your product with the manufacturer's benzoin. Comes out very sharp, 135 to 137, which means your product is benzoin. Now, this is another mixed melting point where you take your product and you mix it with the commercially purchased, the manufacturer's Nesso mixture. 127 to 132, that's much broader range. So you're going to conclude your product is benzoin. All right, I just want to point that out, and all of this is calculation. Now, when you get to your percent yield within reason of what you expect, always think about side reactions. Your side reaction, if because you're concluding that your product is partially reduced benzoin, your side reaction could have been a fully reduced hydrobenzoin. You don't know if it's meso or plus minus. You're not going to form both, but it could be a side product. So if you're not getting a very high yield, then maybe you've formed a fully reduced product. That's kind of how you want to approach this. Okay? Does your melting point obtain tell you your product is benzoin or hydrobenzoin? It tells you it's benzoin from the mixed melting point. Cite additional evidence. We will talk about that. We'll talk about all of this, for which I'm going to jump back into the other screen. But I see why is the melting point higher when it's mixed? It's not really higher. It's actually lower, I think, Aja. It's actually dropping to 127. So 127 is lower than 135. the second melting point. So if you get a high yield of the product, this one, benzoic mixture, no, it's not higher. The product is 132 to 134. This is 135 to 137. It's not higher. It's just a different, sharper range. It's only a 2-degree difference. I think you're talking about this. It's not a higher range. It's not going any higher. I mean, it's slightly off. Instead of 132, it's coming at 135, but that's just maybe a technique issue. So are you convinced, Roger? Let me know. Because it's not really higher. I think it's still a very sharp range. This is not very sharp. This really drops. High percentile, sorry. If you get a high percentile, then just say that your side reaction didn't happen. Sodium borohydride just brought about a partial reduction. If I would say a high percentile is 80% and higher, but if you get something less than 80%, like 60%, 50%, then just say there's a side reaction, and a possible side reaction is a fully reduced benzyl. So Samantha, let me know, okay? Let's look at other evidences, and then we'll come back to this, okay? So for other evidences, there is something given here. I'll jump back to this. It says, while answering these questions, assume the IR showed a broad hydroxyl and a carbonyl. So you have a partial reduction. You're still seeing a carbonyl, but then I just took some IRs for you to kind of use them. So this is benzyl. So this is the IR of the benzyl. So all you should see is a carbonyl stretch. And right there is a carbonyl stretch. So let's say 1700 doublet wave numbers for your symmetric and asymmetric stretches of your carbonyl. That means both carbonyls stretching in the same direction, or the carbonyls, the bonds stretching in the opposite direction. So you should see a doublet here, 1700, that's for the benzyl. So if you have complete reduction, that should completely disappear. This is your benzoin, which is your expected product. You still see the carbonyl. And this one is at 3400 wave numbers. It's not like your typical hydroxyl. This is a little bit sharper, maybe due to hydrogen bonding or lack of it, you know. Actually, the sharper one is a lack of hydrogen bonding. Because typically hydroxyl groups are hydrogen bonded, and that makes it more polar, and you get a broad peak. You don't get such a broad peak, that means you don't have hydrogen bonding. And that's your hydroxyl, that's your carbonyl at 1700 wave numbers, that's your partial reduction. So lab flow tells you that you see a peak for the carbonyl and the hydroxyl. So you can conclude that your product is benzoin. This is your additional confirmation, which is what you would have done in the lab because it's so much more effective. If you get a complete reduction at 1700 wave numbers, absence of carbonyl peak, and right here is 3400 wave numbers, 3500 wave numbers. You see the hydroxyl peaks. That's your plus minus. This is your meso, which is your RS and SR. This one is your RR and SS. Your stereogenic centers, carbons are right here. So again, 1700, absence of carbonyl, hydroxyl peaks. So these IRs will help you, and you can certainly attach them. The key IR here is this one, because you're clearly told that you're seeing a peak for hydroxyl and the carbonyl. So the product IR would have looked like this. So this is your key IR. So this must be attached, okay? So just upload this as your additional evidence for that question. Whether you want to upload the others or not, I'll leave that to you. Whatever is technically easy is what you're going to do. So cite additional evidence for your answer. That's where you'll do that. There are multiple products. Comment on finding the mixture melting point of the products. Your product is pure. It's not a mixture because you're getting a sharp melting point. It's not in the same exact range, but it's not too off. 134, 135, 137, that's kind of expected, because benzoin that was purchased from the manufacturer may not have used your synthetic protocol. You'd have used a different protocol. This is not the only way, that's not one way to make benzoin. So that can all affect, because every time you manufacture something, you make something, it's always going to be contaminated with some side products. You try your very best to remove it. It's never 100%. It's 99.9% pure. That 0.1% can cause these small differences, the instrumental changes, what instruments you use, all of that. So I would say that your product is pure and it's benzoin. If there were multiple products, IR would be the most effective way to find out whether your product is pure or not. So what you may want to say here is the other possible products are meso and the plus minus racemic hydrobenzoins, and those can be identified from TLC and from infrared. And here you could upload those pages. You can upload them all over there, okay? That should take care of the lab flow. Take a couple minutes, just make sure you're okay with all of this. I think that covers everything there. There's only one Spartan for today. While you're looking at that, and if you have questions, I can always back up, so don't worry about it. I've already built these files and uploaded it. If you're not, you should download them to your computer and open them in Spartan. If you don't attempt to open it directly in Canvas, it probably won't open it. But I'm sure it'll let you download and open. I've given you 3 files. One file is labeled acetone and 2-propanol. And then we got methyl acetate trifluoroacetone. You got 2 more files. So what I want to show you is what's happening here. I've already built them. I've calculated them. I just want you to analyze them. Hopefully that removes the stress of building all these molecules. But what I've done is built the ketone and the enol form. So I'm going to jump here to show you. This is acetone. This is propene 2O. You can also say 1-propene 2O. All of these are fine. So, but this is the ketone form or the keto form, and this is the enol form. So I've constructed it, I've modeled it, I've obtained the energies. For obtaining the energies, I used the PM3 calculation for all of them. I was consistent. You're going to say which one is more stable. Okay, and whether it matches with the theory. So let's take a look at one of these, and then I'm sure the rest will make sense. So I'm going to open Spartan here. We'll look at that. So there's acetone, and there's your, your enol. So what you want to do is go to display, go directly to spreadsheet. You can certainly go to properties and get the energy, but I say just go to spreadsheet, because in the spreadsheet, you'll see the energy. So that'll give you an idea. 216 is minus 216 is a smaller number than minus 147. So acetone has a smaller energy than 2-propanol. Okay, so that much we are clear. Then what you want to do is go into lesson 8. We'll answer a question, and that should give you an idea. Let's go to student view. Okay, it's taking too long. I think I may have the questions. here. So calculate the energies. You're asked to calculate. I've already done that. So you're simply going to write the energies. And I think I have a question on which one is more stable. Okay, what are the energies for acetone and 2-propanol? What is the keto-enol energy difference? So for the energy difference, be careful. I know you can do this pretty well. You guys are smart, but just when you get busy, so make sure it's minus 147.67 plus 216.25, minus of minus, right? You know what that is. So you will get the difference of those energies. So put that there. And you'll do the same thing for methyl acetate and its enol form. And I've given you the file for that. You'll do the same thing for the trifluoroacetone. And finally, you'll comment what is the effect what effect does replacing a methyl group with a methoxy group, and what effect do you have in replacing a trifluoromethyl group? So that's what I want to look at with you, just kind of quickly. So for which I want to look at methyl acetate and then trifluoroacetate. So that's your acetone. So methyl acetate is going to look like this. So you're going to have your CH3, C double bond O, OCH3. So I want you to realize that what I've done in my construction is taken, okay, I'm not on the right screen. I've taken that methyl group and replaced it with OCH3. So this is your methyl acetate. I've already constructed this, and I have the enol constructed as well. So see what difference this does. This is an electron donating group. Then what I've done is the other thing is the trifluoroacetate. I've taken that CH3 and replaced it with CF3. Now this CF3 is not an electron donating group, it's an electron withdrawing group. That's all it is, okay? So I also have the enol form of that. So your comment is going to be what's going to happen, which is going to become more stable, ketone or enol. In this case, the ketone form is more stable. If you have an electron donating group, which one is going to be more stable, the keto or the enol form? Electron withdrawing group, which one is going to be more stable, keto or enol? Then what's going to happen to the difference between the keto and the enol form when you go from a methyl group to a more electron donating group, go from the ethyl group to an electron withdrawing group. So you're only going to analyze. I hope that'll be okay. So take a quick look and let me know if you have any questions with any of these. So I have the others done as well, and you should be able to open those without any problem. So for example, this one is your methyl acetate. This one is the enol form. Go to display, go to spreadsheet directly, and you'll see the values there. Okay, so you don't have to work with properties, which is a little bit more cumbersome. I've just added them to the spreadsheet. Similarly, you have the trifluoroacetate and you'll add that. Okay, and then we have 3 more spartans, and we'll get those done over the next 2 weeks, and we'll be done with our lab with the carbonyl compounds. Okay, so that completes our Spartan. I would like you to take a look at everything and let me know if you have any questions. I'll turn off the recording for now, and then I will answer your questions. I'm going to take just